Section 7, let's look into an exciting topic, adding analog assertions to our SystemVerilog OOP testbench. Is it feasible to assert analog properties of the DUT during a simulation run on a commercial logic simulator, a digital logic simulator like Excellium or VCS? Various ad hoc approaches have been tried across the industry, including language extensions like Verilog AMS, and simulator-specific constructs added to a netlist file. We'll demonstrate a seamless approach based on XModel primitives. In this simulation run, we're asserting that the bias voltage VBN reach its nominal level of 700 millivolts, plus or minus 50, at an appropriate time. We can check that here just after the active high reset has deasserted, or we could check it here after the DUT has recovered from power down and is resuming normal filtering operation. We can also assert current values. During power down mode, the supply current to the DUT should drop from its normal milliampere range down into the nanoamperes. Here we've deliberately injected an error in the code, however, so this assertion fails as indicated by the downward red arrow. A big advantage of these analog assertions is that they can verify key analog properties of your design, not only currents and voltages, but also rise times and thresholds. The way it's implemented is by adding a few XModel primitives to our fixture submodule. In this slide, we're seeing only the op-amp portion of the DUT because, of course, the RC feedback network is purely passive. In the supply line, we've inserted an iProbe XModel primitive. That outputs the instantaneous current in the form of an XReal variable, and we feed that into a MeasureMax primitive to allow for fluctuations in time. Using tick and talk, we can start and stop the measurement over a 1 millisecond time span. And the result is the largest real-valued IDD current during that time span. Since this is an ordinary real variable, we can directly reference it within SystemVerilog assertion code, which we'll see in detail in a moment. As far as the bias voltage, to keep things simple, let's assume it's fairly steady. All we really need to do is convert it from XReal type to ordinary real type, giving us an ordinary real variable VBN, which we can reference within a SystemVerilog assertion. Of course, we could make this check more sophisticated, allowing for time fluctuation by using other XModel primitives like threshold comparators to make sure the bias stays above 650, yet below 750 millivolts. Here's our simple assertion plan. The white row describes details of the bias voltage check, and the blue shaded row describes the leakage current check. Let's take a look at the middle column. It's important to realize we don't run these checks continually during an entire simulation run. We trigger them when some antecedent condition is met. In the case of the bias, we're waiting for the active high reset to deassert. Then, starting in the very same clock cycle, we commence checking, as this implication operator indicates. For the leakage current, we wait for the DUT to enter the bypass state. Then in the very next cycle, to allow for settling time, we use this implication operator to commence the checking. Assertions are powerful because they're highly localized. Any downward red arrow tells you that you've got a failure, and you know right away which assertion failed, and it's often going to lead you right to the underlying hardware bug. These are also very handy for catching common interface errors like polarity mismatches or mutually exclusive signals that overlap. They can also document design-specific assumptions like an invalid state. Here's the code for our bias voltage check. Any concurrent assertion must include the keyword property. So here we've declared a name property, biasing with the suffix _pro, and we're asserting it by name. As part of the property description, we need to pin down when the checks occur. These are not continuous time checks, they're discrete time, so we need to identify the edge of some clocking signal. In this case, it's just the rising edge of our packet clock that comes into the fixture via the interface port frequency in. That's when the checks occur. Then to the left of the implication operator, here is the triggering condition, the antecedent. We wait till the reset has fallen. At that point, we commence checking that VBN lies within this range. Question: does SystemVerilog support the use of real variables within a property expression? Well, according to clause 16.6 of the language reference manual, the answer is yes, as long as the overall expression is of Boolean true-false type, the individual sub-expressions can be of any type. So yes, we can use a real variable in our check. Here's the leakage current assertion. We're asserting a name property, Leakage Pro, which is declared here. We're using the same clocking scheme. This time the antecedent triggers when the dot enters bypass state, and then in the very next cycle, we check that IDD is less than 5 nanoamps. That is a little low, and we're deliberately injecting a failure, and we saw the red arrow in the simulation run. We're keeping these assertions simple for tutorial purposes, but because XModel integrates seamlessly with SystemVerilog assertions, you could implement quite complex sequences. This just hints at one where we're checking IDD values throughout a series of 4 clock cycles when the DUT is in the bypass state. So you could define rather complex chains of events using the SystemVerilog sequence keyword. Once you've written half a dozen or a dozen assertions, if they're all using the same clocking and reset scheme, you can wind up with many redundant lines of code. So we recommend using SystemVerilog defaults. For example, we can omit the clocking portion of the property expression by going with the default clock. Here, CB is the name of a clocking block. It's an empty clocking block. We haven't specified any input or output timing. We're simply identifying the rising edge of our packet clock by the synonym CB, and that becomes our default for clocking assertions within this module scope. Similarly, all our assertions should be disabled when reset is active. And so we're using a default disable if and only if clause to specify that as default behavior for all assertions within the scope. And so assertions can be powerful in supplementing our OOP test bench. In the next section, we'll turn our attention to another important topic, functional coverage.